Alright, if you guys could please turn to 2.6 Mathematical Models Building Functions. Example 1. Let p equal xy be a point on the graph of y equals x squared minus 1. Express the distance from p to the origin as a function of x. Okay, so first thing, here we have y equals x squared minus 1. Anytime you're trying to find the distance between 2 points, let me draw what this graph looks like. X squared minus 1 goes down 1, so here's the graph. They're looking for the distance from the origin, right here, to some point xy on the graph. In order to find distance, we're going to use the distance formula, which is x2 minus x1 squared plus y2 minus y1 squared. Now we know x1, y1. x1, y1 is 0, 0. So if I plug in here, if I plug in 0, 0, I end up with x squared plus y squared. And I know that y is x squared minus 1. So I'm going to plug that in. So now I've got x squared plus x squared minus 1 squared. Okay? So if I FOIL that out, I end up with x squared plus x to the 4th minus 2x squared plus 1. X squared minus 2x squared. I have x to the 4th, x squared minus 2x squared is negative x squared plus 1. Okay, so this is my function. This is part A. Okay? What is the distance? What is d if x equals 0? Well, if we plug in 0 for x, we get 0 to the 4th power minus 0 squared plus 1. The square root of 1 is just 1. If I plug in root 2 over 2, d of root 2 over 2, that gives me, let's see here, root 2 over 2 to the 4th power minus root 2 over 2 squared plus 1. Let me scroll down a bit. Root 2 squared is just 2. And since this is to the 4th power, we have root 2 times root 2 times root 2 times root 2, which is 2 times 2, which is 4. 2 to the 4th power, that's 2 times 2, which is 4, times 2, which is 8, times 2, which is 16. Over here, root 2 squared is just 2, 2 squared is 4. So now we have 1/4 minus 1/2 plus 1. I'm going to get a common denominator for everything. If I multiply top and bottom by 2, I get 2 over 4. If I multiply top and bottom by 4, I get 4 over 4. So now I just go with the numerators. 1 minus 2 is negative 1 plus 4 is 3. So I have the square root of 3 over 4, which is the same as root 3 over 2. There we go. Alright, you guys go ahead and try the U-try. A rectangle has one corner in quadrant 1 of the graph on the graph of y equals 25 minus x squared, another at the origin, a third corner on the positive y-axis, and a fourth corner on the positive x-axis. So it looks something like this. Okay? But we don't know where this point or this point actually are. These are just estimations. The only points we know are this point, and this point. These other 2 points could move anywhere along the positive x and positive y axis. So, express the area A of the rectangle as a function of x. Well, okay, so you need to think, how do you find the area of a rectangle? Hopefully you guys know the equation. Length times width. Okay? In this case, your length is just going to be your x. Your width, or your height in this case, is your y. And you know your y, you know that y equals 25 minus x squared. So I'll write this out. X times y, and we know that y equals 25 minus x squared. So x times 25 minus x squared. If I distribute the x, I get 25x minus x cubed. Okay? So this is part A. Part B says, what is the domain of A? Since xy is in quadrant 1, like it says, where's my cursor? There it is in quadrant 1, we have x is greater than 0. Move down here a little bit. Also, y equals 25 minus x squared has to be greater than 0 since it's also in quadrant 1. So, if I subtract 25 to the other side, I get this. If I divide by -1, I need to flip the sign. So x is less than 5, and x is greater than -5. Okay? So, combining these restrictions, we know that the domain is from 0 to 5. Okay? And this is obviously because x is bigger, or less than 5, bigger than -5, but we also know that x is bigger than 0. Okay? Part C says graph a equals a of x. Okay, so I'm going to pull out my calculator. Alright, so I've got y equals, let me scroll up to my equation. There it is. I've got 25x minus x cubed. There we go, graphing it. Okay, I'm going to change my window a little bit. Let's back up to negative, I don't know, 30. And I'll go every 5. Oop, not every 55. There we go. Let's try again. You know what? I might even try something different. I'm going to stretch it vertically and compress it horizontally. So let's try -50. I'm sorry, that's for the y. For x, let's go from -5 to 5. We'll go every 1, but for the y's, we'll go from -50 to 50. And I'll go every 10. There we go. That's a little bit better. Okay. Hopefully you guys get pretty good at playing with your windows and such. So this is what we have for our graph. I'll pull that up. Okay. I'm going to go ahead and just draw a quick sketch over here. Okay. Okay. And then the last thing says, where is the area at its maximum? Okay. Basically, where is the value the largest? Oops, my bad. Okay, so what I'm going to do here, I need to find the maximum value right here. So I'm going to go second, calc, maximum. Here, left bound. right bound. Maximum x equals 2.89. Okay. And 48.11. 2.89, 48.11. And I already forgot the y term. 48.11. Okay. Okay. So when x is 2.89, the area is 48.11, and that's the maximum. Okay? Alright, I'll let you guys try this one. Alright, last one. A manufacturer of children's playpens makes a square model that can be opened at one corner and attached at right angles to a wall or perhaps the side of a house. If each side is 3 feet in length, the open configuration doubles the available area in which the child can play from 9 square feet to 18 square feet. See figure 64 below. And I don't think here's figure 64. And this is figure 65. Okay. Now suppose that we place the hinges at the outer corners to allow for a configuration like the one shown in figure 65. Build a model that expresses the area A of the configuration shown in figure 65 as a function of the distance x between two parallel sides. Alright, let's do that first. Let's take a look at figure 65. The area A that we seek consists of a rectangle and an isosceles, and the rectangle obviously has a width of 3 and a length of x. Okay, so the area would be 3 times x. It also consists of an isosceles triangle with base x and 2 equal sides of length 3. Okay, the height h of the triangle may be found using the Pythagorean theorem. Let's go ahead and do that. So I've got a squared plus b squared equals c squared, so h squared, that's our a. This would be x over 2 since the whole thing is x. X over 2 squared equals the hypotenuse, which is 3. Okay, so what I'm going to do is I'm going to solve for h here. I've got h squared equals 3 squared minus x squared over 4. Okay, and that would equal 9 minus x squared over 4. I'm going to multiply top and bottom by 4 to make it one fraction. So I've got 36 minus x squared over 4. Okay. So h, let's see here. Straight over here. H of x equals 1/2 root 36 minus x squared. And the 1/2 is because when I take the square root, the 4 becomes a 2. Okay? Alright, so that's my model. Find the domain of A. Well, the domain, this has to be greater than 0. So 36 minus x squared has to be greater than, or actually not even equal to 0, just greater than 0. If I subtract 36 from both sides, I get negative x squared is greater than negative 36. I divide by negative 1, this changes. And then we have something very similar to the problem before, where x is bigger than negative 6, x is less than positive 6. Okay? Now, because x is the length of a side, we also know that x has to be greater than 0. So using these two things, we know that the domain is from 0 to 6. And I apologize I didn't give you guys more space. You're welcome to work on the second sheet of paper. Find A if x equals 5. Okay, if you plug in 5, you get 36. Actually, let's go over here. If you plug in 5,